Struggling with math? You're in the right place. Welcome to Explaining Mathematics, the channel where we simplify tough problems, break down complex formulas, and turn confusion into clarity. From basics to advanced topics, we explain it all step by step. Let's start solving.
All right, today we're going to crack a code. It's a code that's literally hidden in plain sight, a mathematical language that shapes pretty much everything in our modern world. And yeah, we're talking about polynomials.
So let me ask you a question. What in the world is the link between the beautiful curve of a bridge, the exact trajectory of a rocket launch, and the amazing graphics you see in a video game? I mean, on the surface, they seem totally unrelated, don't they?
Well, here's the secret. They're all described by the exact same really powerful mathematical language. You can think of it like an underlying blueprint, one that governs the shapes and systems that are all around us.
And that's exactly what we're diving into today. So let's forget about all those dry textbook definitions for a minute. We're going to treat polynomials as what they actually are, a practical, hands-on code that literally builds our reality.
So let's look at the code itself. This right here is a classic polynomial. And I know, at first glance, it might look a little intimidating. But don't worry about that. The most important thing to get is that it's just built from a few super simple parts. Kind of like Lego blocks, actually. And once you see them up close, they're surprisingly easy to understand.
Okay, so let's break this thing down. Imagine we're taking apart a recipe to look at each individual ingredient. That's what we're going to do right now. We're going to deconstruct this expression to see all the basic components and figure out what really makes it tick.
All right, first up, we've got what are called terms. A good way to think about these is like the individual items you'd put in a shopping cart. They're the main chunks of the polynomial, and they're always separated by plus or minus signs. So in our example here, we have three separate terms, 3x squared, negative 5x, and 4, and each one has its own specific job to do.
Okay, next up is the variable. In this case, it's our x. This is the really dynamic part of the code, you know? It's the ingredient that allows for change. Its value isn't set in stone, and that's precisely what gives polynomials their incredible power, because they can describe things that move and change, like the arc of a ball you throw, or how an investment grows over time.
Now, that number you see multiplying a variable, that's called the coefficient. You can just think of it as a scaling factor. It basically tells you how much of an effect that variable has. So in the term 3x squared, the 3 is essentially dialing up the impact of whatever x squared ends up being.
And finally, we've got the constant. This guy is the anchor of the whole expression. It's just a fixed number that gives us a solid starting point. It doesn't change no matter what x is. It just provides the stable baseline. And in our example, that's the number 4.
Okay, so we've got our ingredients: terms, variables, coefficients, and constants. Now let's see how they actually work together, because the real key here is learning how to combine and simplify them. That's what makes these expressions so powerful, but also manageable and, well, easy to work with.
The big secret to simplifying polynomials is this one little concept called like terms. And it's a super simple but absolutely vital idea. Here's the deal. Terms are alike if they have the exact same variable part raised to the exact same power. The number out front, the coefficient, can be totally different, that's fine. So 5x and negative 2x, they're like terms. But 5x and 3y? Nope, not alike.
And combining them is really just a straightforward three-step process. Step 1, you spot the terms that match. Sort your apples from your oranges. Step 2, you group them together. And step 3, you just add or subtract their coefficients. So if you have something like 4x plus 3 plus 2x minus 5, well, the x terms go together, the plain numbers go together, and the whole thing simplifies down to a nice clean 6x minus 2.
Okay, so this brings up a really important question. Can any old expression with letters and numbers be called a polynomial? And the answer is no, absolutely not. There are some very specific rules you have to follow to get into this club. And honestly, there's one single rule that's more important than any other. To officially be a polynomial, the exponents on the variables have to be non-negative integers. We're talking 0, 1, 2, 3, and so on. That means no negative exponents, no fractional exponents, which is what square roots are, and definitely no variables hiding out in the denominator of a fraction.
So let's look at some examples. Over here on the left, you see perfectly valid polynomials. See how they all have those clean whole number exponents? But on the right, well, These are the rule breakers. We've got one with a negative exponent, another with a square root, which, like I said, is just a sneaky fractional exponent, and a third with a variable down in the denominator. None of these guys get to join the polynomial club.
All right, so once an expression passes the test and we know for sure it's a polynomial, we can start to classify it. And mathematicians have a pretty handy two-part naming system just to keep everything neat and organized.
First off, you can name them based on how many terms they have, which is super intuitive. If it's just one term, it's a monomial. Got two terms? That's a binomial. You know, like a bicycle has two wheels. And with three terms, you've got a trinomial, just like a tricycle. It's really just a simple shorthand for how many pieces it has.
The second part of the name, and this one is often way more useful, comes from its degree. The degree is just the highest exponent you can find on any variable in the whole polynomial. So a degree of 1 is called linear. A degree of 2 is quadratic, and degree 3 is cubic. And these names are important because they tell us a ton about the shape of their graphs and how they'll behave.
Okay, so we've defined all the parts, we've learned the rules, and we've even figured out the names. But let's be real. Why does any of this actually matter? It's time to bring this all full circle and connect this mathematical code back to the real world, right where we started.
And this quote right here, it really just nails it. It gets to the very heart of the matter. Polynomials aren't just some abstract exercises you do in a classroom. They are the actual tools used to build equations that describe and solve real problems. Everything from simple word problems to mind-bendingly complex scientific challenges. And their reach is just incredible. I mean, the reason they're used everywhere is because they're pretty simple to calculate, but at the same time, they're powerful enough to approximate almost any shape imaginable. Engineers use them to design that perfect stress-distributing curve on a bridge. Physicists use them to predict a rocket's exact trajectory. And seriously, every single time you watch a 3D animated movie, what you're really seeing is countless polynomial functions all working together behind the scenes to create those smooth, believable shapes and movements.
So, when you boil it all down, this elegant mathematical code, it isn't just something stuck in a textbook. It's literally built into our bridges, it's rendered in our video games, and it's woven deep into our understanding of the universe itself. It's a fundamental language for creation and for discovery. And that really just leaves one last question for you. Now that you know the code, what are you going to build?
If this video helped you understand the topic better, don't forget to like, subscribe, and turn on notifications so you never miss a lesson. Comment below what topic you want explained next. Thank you for watching Explaining Mathematics. See you in the next problem.